Okay, welcome back everyone to this new session this afternoon, which is going to be about workshops. So we're going to start with a workshop by David Braun, and it's going to last about an hour, and then we'll have another workshop by Miller, and then we'll take a break for 30 minutes, and we'll have a final workshop with Celeste. And that's kind of the program for this afternoon, and maybe after that we can all go for a drink somewhere else. So yeah, again, like about an hour. You know, like I think time is slightly more flexible this afternoon than this morning. So you know, like I guess 3:10 or something like this. So yeah.
Or okay. Thanks everyone for sticking around for the workshop. This is going to be pretty technical, but I want to work with everyone's comfort level. So I want you to interrupt with questions and try to make it more interactive, because if you don't, then I'm just going to, you know, walk through a lot of code, and it could be boring. So I'm trying to be receptive to how you're feeling about it, and we can move on to a lot of other topics. It can be a kind of open-ended discussion. So maybe I'll start there. Like, are there leftover questions from the morning session from anyone? Yeah.
Did I get it right? Wait.
Oh. If you say it out loud, I'll repeat the question into the mic too. I can just do that.
I think we need
yeah.
Otherwise, people in the streaming won't hear anything. So. It's good after lunch.
Yeah, thank you for the presentation once again. And did I understand right that you're working on a system that is able to figure out what signal path structure on the underlying signal generation could explain a certain signal?
Yeah.
That you give it as a target signal and reproduce it kind of?
Right, yeah, it's a pretty challenging problem, so I don't have a solution yet, but I'm working in that direction. The beginning part of the morning talk was talking about optimization and machine learning. So for a given DSP, how do we optimize the numbers that are used in that DSP? But then that latter portion of the talk, I was trying to say, how do we explore the space of all possible programs, all possible topologies of DSP? You know, to decide that this parameter needs to be modulated by an LFO, and the thing that's driving the frequency of that LFO needs to be an envelope, and so on. So it's a very open-ended and large design space. You know, it's basically the space of all designable programs, which is enormous. But we're trying to, first of all, restrict it to an audio DSL to say we're going to work with Faust, or more specifically, we're going to work with the Faust box API. And then, moreover, we're trying to continue to clamp it down further and say we're focused on the design space of modular synthesizers. And now, for even narrower than the space of modular synthesizers, you might say, I only care about these specific modules, and I only care about, and so on and so on. And you keep restricting the design space, and that is an essential part of program synthesis, using domain expertise in order to restrict the search space and also traverse it more intelligently. Yeah. So on the topic, something that I brought up at the end of the talk was that paper that was the blind estimation of audio processor graph. So I think that you know, using the Faust libraries to improve that line of research and to do to have generative procedures for making these audio processor graphs, to get instruments involved too, and then also to have it be differentiable. That's a really, I think, promising line of research in the future.
So we could think of a future where you take a finished track from a DJ or something, and you put it into a system which outputs like an Ableton Live file that you could open, and where you would have like the whole recreated track, kind of.
Yeah. So, I mean, that brings me to this topic here, which is this GitHub repository that I'm showing you, which is called DAW Dreamer. So I started this in 20. That's.
I mean, I don't want to take too much of your time with that, but.
No, I'm answering your question.
Okay, good. Thank you.
Yeah. So I think that This project Daydreamer is kind of the idea that one of my main goals in however many years it's going to take me to do it is to work on something like that, as potentially nefarious as that sounds, to have a song and to deconstruct it, or as another researcher, Cristani, who has called it, to decompile music, to take an existing track and to decompile it into everything that's going on, the separate tracks, what instruments and effects are used on each track, and what are the parameters of those things, and to just do full analysis and reconstruction of music. So yeah, I think that I think of the DAW itself as a kind of reinforcement learning environment in the same way that Atari and Go are video games. I mean, you don't necessarily have to use reinforcement learning, but to just think about DAW as an environment in which agents can take actions and listen to the results and have this crazy feedback loop, I think that that's just a kind of pipe dream, but that's why it's called Daydreamer as a project. Yeah.
Thank you.
Yeah.
Like we're just thinking about it during lunch, and like I was just wondering if one would have something like a synthesizer 808 or something, and like how difficult it would be to like just play something and turn all the knobs and do all these things and then recreate all the action or the user interactions that happened only on this one instrument.
I'm sorry, I didn't understand, I think.
Like if you have a synthesizer, like a physical synthesizer, like an 808 or something, there are a lot of like simulations of that also. Like if you just have like someone play with that thing, do you think it would be easy or a good step towards this direction to recreate all the user interactions with the instrument just from the file? Because then you can like simulate everything and you have like a very limited testing space basically, because it all comes only from one instrument and you know all the interaction possibilities.
Yeah.
But I think this in my imagination, this could be a very nice step to also do it like instrument specific, basically. But do you think this could work? Or?
Yeah, I think that brings to mind something else going on in this AI space, which is using kind of version control, as in software source code development, to inform how code can be improved over time. And so you have people scraping GitHub or looking at vast amounts of Git trees and the log records to the files, and they look at the git diff message and they say, what this git diff does or achieves is what is in the message. So they are coming up with these machine learning models that can take a message and predict the code change that was necessary to do something. And so the same thing is possible with synthesizers. If you have a human with all of our prior knowledge about what it means to interact with knobs and to explore what a synthesizer is as an instrument, you can have a record of the decisions that they make, and that would be like behavior cloning in the realm of reinforcement learning, to teach an agent to mimic what a human does to explore a synthesizer. So that's definitely something that I think people are looking into. I think that as of now, there still aren't a ton of reinforcement learning synthesizer projects, but it could happen, and there could be a big new wave of people doing it that way, I think.
Thank you.
Okay, so that's great. Please interrupt me with more questions. I enjoyed that very much. So we are looking at this GitHub repository called Daydreamer, and I want to show you, so if you have a laptop, please follow along, and because we're eventually going to be doing a Google Colab where you're going to run stuff in the web browser. So get to this page, github.com/dbraun/Daydreamer, and I'll show you just a quick basic example of Daydreamer. So we can import Daydreamer as DAW, and now we import SciPy. You're not actually running this code, I'm just telling you about it out loud right now. So we create a render engine, and a render engine can load a graph of processors. We give it a sample rate and we give it a block size. So here we create our first processor, and we can have unlimited Faust processors. We can also have plugins. So you can load a VST plugin, and you can load, those are the two most important ones, but you can also use simple processors for changing to mix the loudness of multiple inputs. So let's focus on just the Faust processor now. So we can specify our DSP code here as just a plain string, or we could load it from a file. And here we create an example called mySign. We declare a slider, and we declare a volume. And then we use the basics library for dB decibels to linear scale. So we have a frequency, and that goes into our oscillator. We multiply by a gain, and it's split out into stereo. Now, if I do get parameters description, then we're going to get a list of, it's going to be a list of dictionaries where each dictionary is a parameter. So you would get information to know from your Faust processor that the possible parameters that you have to manipulate are named frequency and volume. Here we load the graph, and then we set the parameters. So here the value was 440, and we just set it to 440 again. And here the volume started out at 0 dB, but we change it to -6 dB. An interesting feature here is that this could be a NumPy array. So if you wanted to say, I want my volume to be a sine wave or to be a linear ramp, rather than passing a single number here, you would instead call set_automation instead of set parameter, and you would pass that NumPy array. So this is a programmatic way of kind of interacting with the DAW. You know, there's no GUI here. It's not nearly as nice as something like Ableton, Logic, Fruity Loops, whatever. But it's a programmatic way of building audio processor graphs and specifying the automation curves for those processor graphs. So even if you're not doing anything involving the machine learning frameworks that I'm going to show you later, this is just a relatively high-level way of scripting and batch processing audio. So you're not using a GPU to do anything clever here. You're not doing backprop. You can just do this to take MIDI files, take a database of MIDI files. Maybe you would augment your MIDI files in some way, like using Music 21 or some other library, and you can render vast amounts of audio. And then you use that for source separation or any other MIR, music information retrieval task. So I think that this, there is an existing library called Pedalboard from Spotify that is quite strong at using plugins. And you know, I commend them for that. I think that one of the strengths of DAW Dreamer relative to Pedalboard is that it supports Faust. So you can, under the hood, it's using LLVM, low-level virtual machine, in order to render the audio, and you can also scale that up in terms of using multiprocessing. So it's pretty strong in that regard, and we all love Faust, so that's why I'm glad that it supports Faust. So there's some other examples here. You know, this is showing how you can add a MIDI note. So you specify that you want the pitch to be 60 and a velocity of 100 for the note to start at 0 and for it to last 2 seconds. And I could have also said, I want to load a MIDI file. And then when you load a graph, this is a synth, and then the synth is going into an effect. The effect could be a plugin. So like you're specifying the effect path, and this is a DLL, like a VST, on your Windows operating system. And then you load the graph, and then you render audio. So yeah, I think it's a good scriptable way of making music. Any questions about this? Yeah.
What is the path for this
These are placeholders. You change this yourself based on the specific plugin on your computer that you want to use. So this could be a .vst file, or it could also be a .component file, like on macOS. .component is a plugin type. Yeah. Also, the BPM feature is interesting. So you can actually set the BPM, and now your plugins, which can be BPM dependent, will respond to that. And you can even set an automation of the BPM. So this could be really interesting for making a data set that you use for beat tracking, because you could take something that's very rigid in terms of its timing, but you could add subtle variation with a NumPy array specifying that I want the BPM to, you know, be roughly 120, but with some human timing where the drummer is imperfect, and it's ranging between like 119 and 121 with noise. Yeah. Yeah. What is it a typo or?
Yes. The second one.
Oh, thanks. Okay. Thanks. I'll fix that later. Yeah. Yeah. And then you'll be a contributor. Yeah. Okay. Any other questions? Yeah.
Does it allow you to do real-time stuff?
No. And that is something that pedalboard can do. So that's definitely a strength of pedal boards. Yeah. There are plenty of issues. I'm not shy about that. You know, plenty of bugs, plenty of requests. Most of them are related to people saying this specific plugin doesn't work, and it's kind of out of my scope as like a researcher to support every plugin that exists in the world. But I've put in a reasonable amount of effort into supporting plugins. So if you want really good plugin support, go to pedalboard. Okay. So yeah.
How do VSTs and the Faust code connect? Do you
Yeah.
use the VST as a Faust?
Right. So the main thing connecting all of this together is Juice. So you know, I give them. There are a lot of licenses involved here. Look at all of the licenses. Juice is involved. Then there's PyBind 11, libsamplerate, and rubber band library. This is what does the pitch warping and time stretching, and Steinberg VST 2 and 3, and Faust. So, but Juice has this class called audio processor graph that they've been working on for a very long time, and that is what is going on. When you say load graph, this is implementing this thing here, synth, is a subclass of an audio processor in Juice terms, and we are calling load graph. And so we're really interacting with the Juice API via Python bindings to dynamically build this graph. And what's interesting is that this works even when your plugins have non-stereo inputs. So you could have a plugin that needs 4 inputs, you know, like a sideband compressor where you have your main, but you have your auxiliary input. And so here, suppose effect expected 4 total channels, 2 stereo inputs. Rather than putting synth get name here, I would actually do get name, comma, and then I would say auxiliary input dot get name. And this is just returning a string. So dot get name here is just returning the same synth argument that I passed here. So this text synth is what shows up here. So yeah, it's a very generic audio processor graph from Juice. Yeah.
And in terms of like API, the sync and the engine responds to the same function as the audio processor in Juice.
Yeah.
Like I see that there are the underscore, but they are like the same. Like they get new input channels and get new output channels.
Yeah.
They are the same of the audio processor.
Yeah, I mean, roughly, if you look at what I've done via the Python bindings, it's kind of just calling the method that exists on the Juice object. Cool. Seems like you're a Juice user, so that's good. Okay, anything else? Okay, great. So next topic is, let's go to the examples. So we're at Daydreamer. Now we're going to go to examples. And there are several notebooks here that I can talk about today, and I'll kind of adjust it, the tempo. So the first one that's highest priority to talk about is Faust to Jax. The second one is the Box API, and this is kind of related to that program synthesis that was the second half of my morning talk. And then there's also Faust to QDAX. QDAX is a quality diversity algorithm for discovering diverse solutions to a problem. And this is that parametric equalizer situation that I mentioned, where you have a parametric equalizer with 10 unknown variables, and we want to use this algorithm in order to figure out what those numbers were. There are some other examples here that are cool. DJ mixing does automatic DJ transitions, where I can have a song at this tempo, and I can have a different song at a different tempo, and I use Faust in order to, and I use the rubber band library to do pitch, not pitch shifting, time warping, so that even as the tempo changes, I'm smoothly transitioning between the songs. This could be really interesting for making a data set of DJ transitions, or to analyze how other DJs are doing stuff where they're using a low-pass filter and changing the cutoff and so on to transition between songs. There's also a mashup generator, and there are examples for using all of the cores on your CPU to render VST one-shots, but VSTs can use up quite a bit of RAM, so you may not necessarily get away with using all of the cores. of your computer. Okay, so let's first go into the Faust to JAX notebook. So I'm clicking here, and then I click on the notebook file. Here we're still on the GitHub page, but now I'm going to click on Open in Colab. So this takes me to Google Colab. So, you know, there's going to be a lot of technical information here. I would say revisit this notebook as much as you want and email me with questions or file an issue on GitHub, stuff like that, so that we can improve it together. This is just an overview that resembles what I did in the morning, what I'm saying here. So we're going to talk about that simple cutoff example where it's static, and then we're going to talk about the automation example where we learn the automation curve. Then we're going to talk about the differentiable subtractive synth, which is a really simple example, and then we'll do the polyphonic wavetable synthesizer, which was much more complicated, but much cooler, I think. So just to show you some other information about Colab, you should go to runtime at the top, and you should go to change runtime type, and you should make sure that you're on CPU. The reason for this is that a CPU at its clock speed is faster than a GPU. So if you care about just getting one item as one example of audio, you're going to get faster results by using the CPU. But if you're doing a large computation where you are kind of using machine learning to do optimization, then you might want to use the GPU because the GPU is doing everything in parallel, which means that if I want 100 items, it could be exactly the same speed as getting 200 items and 400 items and so on. It's just a limit of what your graphics card's memory is. And I've confirmed that in my experiments, but just because we aren't doing a large batch size, we only care about using the CPU in this Google Colab. So that's why you should make sure that you did runtime typing and you changed it to CPU. Also, if you were to do GPU, then you would want to do this code here where I would change CPU to GPU, and then you could use the power of your GPU. Also, installing GPU on Windows is the most difficult thing, but I've done it before. So to use JAX with a GPU on Windows, you have to use WSL. So, and you know, I use an educational license of PyCharm, and PyCharm works really well with WSL. So that would be my recommended approach to Windows GPU and JAX. Yeah.
David, can you, because turns out my collab is in French, so I'm not sure of where I should, the runtime, which is execution, which one? Okay, this one. Okay, no, I got it. Modifier l'exécution. Ouais, l'exécution. And so the recommendation is we stay CPU.
Yeah, use CPU. Okay, so now what you need to know is that this, this is text, and if I click on it, if I double click on it, then I get Markdown, because it's actually Markdown. And I get a live preview on the right here. What's this? This is changing the live preview. So yeah, I'll keep that there. And I have my text on the inside, and I'll hold Shift key, and then I'll press Enter, and that's going to collapse it and bake it down into a text rendering again. So now this is just Markdown, so we're not executing it. And now the very first thing is we do install and setup. So I just have my mouse inside here, and I could either do Shift return, and that runs it, or I could click the play button on the left. So I did Shift return, and now it's installing some stuff, and you can see that it's executing over here on the left. Okay, it's going. So we are installing NumPy and SciPy, Librosa for reading audio files, and then these are all JAX libraries that are related to each other. Okay, so now the next step is to do this one. So here I'm doing the play button to demonstrate this. And it's installing DawDreamer. Any issues so far? Okay, yeah.
It's working on the cloud or on the...
It runs in the cloud. Yeah, this is not installing to your local file system. I think the GPU is also free, but you aren't getting a great GPU. And the other thing is that you will time out. So you can't just run this notebook for 24 hours. It's going to cap your time limit unless you pay for it. And it's $10 a month to pay for the faster one. OK, so now we're importing the libraries. I grouped things together. So these are all JAX related, and then these are all Flax related. Flax is kind of like, you could think of Flax as PyTorch Lightning in a sense for people who've used PyTorch Lightning before. OK, so now we're executing this one, and I'm just going to. You don't have to mouse click every time you do this. You can just hit Shift, Return, Enter, and you'll keep going down. So here we got down to the Faust example, which I'm skipping because I'm assuming everyone knows enough Faust. And now we are going to proceed with the following Faust code. So this is just our plain text string of Faust. And we want to convert it into a box, first of all. And we're going to go from Faust code to box, and then from box into JAX code. But before I show you the JAX code, I'm going to show you the C++ code. Now, if you use Faust on the command line, it should be familiar to you where you just type Faust and then mysource.dsp, and that's actually going to return C++ by default, I think. Maybe you have to say -lang CPP. But this is an equivalent Python way of getting that same text information. So we say box from DSP with our Faust code, then we get a box, and we can assert that the box's inputs and outputs both equal 1. You can see that this is a cutoff with 1 input and 1 output. And then we get our CPU code. We could do this alternatively, where instead of using Faust context, we have to create a lib context, and then we have to destroy a lib context. So anytime you use boxes or signals, it has to be in this safe sandbox zone using Faust context or lib context. So that's a kind of gotcha, but it's not hard to do. I typically have a main function, and then there's the syntax where you do if __name __ equals main, and then you say execute main, but then I just say with Faust context execute main. So anyway, that's one way to do it. So we got our C++ code, and then we print it. And now this is the C++ code of our low-pass filter with a cutoff. And I'm going to scroll down, and we see a compute function. And the compute function has a number of samples to generate. And we have a for loop with that number of samples. And here we have the main one pole logic. Outside of that, these are where the UI parameters are used, and that's why they're given this name slow, because they're only updated once per block size. OK, so that was C++. Now let's look at the JAX code. So I executed the next box, or the next code section that looks like this one. And now we have a full Faust or JAX example. So it starts with the Faust license, and then it imports some things that are JAX related. And now we get class myDSP. And so the class myDSP is named that because we declared it here, module name myDSP. And and also an important thing of using the box to source function was that we specified an architecture file. So I want to take a poll, please be honest. Who has used an architecture file before in Faust? OK, not a lot, so I want to talk about it more. So when you convert Faust code into an architecture file, you are targeting a specific kind of application. So sometimes you want to support various device drivers and codecs and things that like to work with Jack or various things with Linux. And so you're telling the compiler to use more specific things when you're doing a code conversion process. So in C++, there are many variations of this, many different architecture files to use. JAX right now only has one architecture file, so that's minimal.py. But minimal.py, maybe it can be expanded in the future. Maybe talk to me one-on-one about how we can make variations of architecture files. So It's kind of a template that is being filled in when we're doing our Faust to JAX conversion. Yeah.
So I saw that you still have the Braun copyright, but
Yeah.
you wrote this architecture file, so there's no copyright for that.
Okay.
Really?
Oh, you mean like Graham doesn't own it, I own it?
Yes, you can write every architecture file that you want.
Yeah.
So the architecture file, the copyright is the copyright of the one who wrote the architecture file.
Okay.
So since you wrote it, you can put your own copyright.
Okay, that's good to know. Sure.
So basically, the copyright system in Faust is what's going in is what goes out.
Yeah. So I could have put David Braun, give me $1 million if you use this code here, but I didn't because I like you. Okay. Yeah, better decision. So now let's this is the file, and you could have gotten the same Python source code on the command line. I'm emphasizing that, and it would have been spit out as converted.py or whatever you specify as the argument -o, some Python name. But here we have it as just plain text in this ecosystem. So I'm scrolling down to the most important function, which is tick. So tick is basically equivalent to what the compute function was in C++. So it's important to kind of study this code sometimes, like the hardcore Faust developers who turn their Faust code into C++ code, they're often looking at that C++ code and doing a gut check on whether it looks fishy, whether it looks like it's doing something dangerous or slow, something that could be optimized further. So here we are looking at the tick function to know what is going on in our JAX code. There are some other things in here that I'm going to skip for now, but these mostly relate to loading sound files. So there's the sound file primitive in Faust when you want to load a WAV file and play it back as a read-write table and so on. And so you can override this method, this load sound file, and you can if you were to, you'd have to modify the architecture file. That's what this purpose is. So if you wanted to have a custom way of if you refer to a sound file, but you want to replace it with some magic numbers that don't actually exist in a WAV file, but can just be generated on the spot, then you would override load sound file and so on. And there are other methods in here that come from the architecture file if you look at that yourself. So this is how sliders get created, and this is how n entries get created, and so on. And there's near final thing I'll say about this is that there is a test function. So if you were to convert your Faust code into JAX and run it on the command line, by default, it would be using this test function. So that's a good thing. And we use that for confirming that the outputs of the JAX conversion process actually match what C++ does. So you can rest assured that this Faust to JAX conversion process is actually robust because we've compared it to exactly what the C++ code does numerically and made sure that with floating point precision, it's actually generating the same thing that C++ does. So yeah, so this is our code that got generated, and this is everything that I talked about earlier, where you could have named it myjaxcode.py, and you could just run Python myjaxcode.py --help to understand how to use it on the command line. And if your file that you generated on the command line was called myjaxcode.py, then in some other Python file, you could say, from myjaxcode, import myDSP, because our class was named DSP. And then you instantiate myDSP, and then you use that as a trainable neural network in JAX. This is very similar to what the other popular PyTorch libraries are doing. They're making individual files where each file is a DSP, a differentiable DSP class. Like they have a class that has a compressor module and a stereo effect module and so on. But all of those modules were coded by hand and are kind of prone to error, I believe, or maybe not that efficient. But if we use the Faust to JAX conversion process, then we can rely on all of the tested Faust code in the Faust libraries, and you don't have to bother manually differentiating code. Yeah.
So you say you make a neural network from the program, but
Yeah.
Is it the cutoff?
Yeah.
Or is it not cutoff?
It depends what existed in this file here. So if Faust_code.dsp had an H slider in it, then this myDSP object here would have a parameter in it, and you don't have to think about that at all. Does that make sense?
I'm not sure I get what are the parameters?
Yeah, okay, I'll show you that. So if we look at this is the auto-generated Python code. So the important thing here is build user interface. So this mimics what is done in C++. So
the parameter is the user interface.
well, let's look at this method, build user interface. You could see any number of lines here for every parameter that existed in your Faust code. So one parameter was named HF for float, H slider for horizontal slider, and then it's given the unique identifier 0. And we don't have to think about that. We didn't name that ourselves because it knows that it's named cutoff. But to give it just a more like unique name, it's given H slider because that's what the convention is in the architecture files. So you'd end up with any number of objects here, and each one calls add slider. And if you want to customize how add slider as a function works, then you do that in your architecture file. Okay, so I think I talked about this, and now this is some of the trickiest stuff in this entire notebook is understanding what is going on in this section. So I think that you really have to be motivated to learn about JAX to learn some of this stuff because it's really confusing. VMap is what takes a single item and it turns it, I think it vertically maps it into a batch. So you write your code and you just, suppose you wanted to have multiple things of that function executed in parallel, VMap is what helps you achieve that. So when we create the DSP class, I left it by default as a non-VMapped class because I wanted to have the user VMap it as an optional thing. So that's why it became necessary here. But definitely email me something or check out the documentation on VMap that I linked to here. Like open that up on another tab and come back to it later because it's very important. It's the essential thing about JAX and VMap and Flax and so on is this feature. VMap is also implemented in PyTorch. It's the same idea. Okay, so back to the notebook. So I execute this item, and then the next thing is I'm going to execute this block, which is actually that one doesn't get executed. But you should read about how pseudo-random number generators work in JAX a bit, so bookmark that and come back to it later. And now we're going to do inference. So we have our DSP class, which we created as, we created a DSP class here. It's called model batch. Our function returned it, and so now we have hidden model. And then hidden model is what we use down here. So hidden model we initialize, and we give it the noise inputs, and these are full spectrum white noise. And then we get parameters, and now we actually pass our parameters to our JIT. JIT is just-in-time optimized function, and then we get audio. So what we're demonstrating here is that the first input is going to be the very loud white noise, and then the second one that I'm going to show here is the result of it being passed through our model, which is going to be the low-pass filtered white noise. So I'm going to play this at a low volume and see what comes out. Okay. It's only coming out of my computer. Maybe I'll fix that later. But yeah. Okay, so the next thing is about path names. And this is to emphasize that when I printed out the parameters, there are two different kinds of parameters. One is normalized and one is unnormalized. We only have one parameter here. It's the cutoff parameter. The cutoff parameter was 440. And so with floating point, for some reason, it's coming out to this not this thing that's close to 440 but not exact. And this is the unnormalized parameter. But the normalized parameter is remapped from its input range of like 20 to 20,000, which is what we declared in our Faust code. And we take that range 20 to 20,000 and we remap it to -1 to 1. And the reason we do this is because it solves an important issue of machine learning, which is known as conditioning. So the conditioning number, it has to do with when you have a valley, and I don't have a hand reference for myself, I think, but if you have two parameters, and you're optimizing two parameters, it's kind of like a valley. And if the valley is very elliptical, then when you follow the gradient, you can do a lot of zigzagging down to reach the bottom of the valley. But if your loss landscape is very circular, then that fixes what's known as the conditioning number, and you're going to have more of a direct path to the center of the valley and arrive at the global minima. So that's why this normalization strategy was necessary. So kind of behind the scenes, the numbers get normalized, but then we have this other procedure that presents them to you, the user, to translate into the human readable range, which is hertz, where it's 20 to 20,000, which is what you assigned as the range of your slider. So here I've kind of just talked through this information that was here, so we can keep moving on. I think also this link is kind of interesting because this is what is doing it under the hood. It's called the SO function, and so we SO our intermediate variables where the values that are being SO'd are the remapped values that are in the human range that we want, that are like the 20 to 20,000 number, not the -1 to 1 number. So bookmark that and come back to it. Okay, any questions so far? Okay, sorry that it's pretty technical. So here, the next thing is maybe more exciting because we're actually going to be training it. So we are going to suppose that our initial cutoff is 10,000. You can actually control this with a slider over here. And you can set the batch size and the learning rate and the momentum. This is just a very naive, I forget the exact optimizer that we're doing, SGD. SGD is the most boring, ordinary optimizer. And so the results aren't perfect, actually. But I think that if you looked at the optax library and picked a different optimizer, then you could get more stable results as the loss approaches 0. So we are going to create all of this kind of boilerplate code that is kind of ugly, and we create a train step. So the train step, importantly, has @jax.jit. So this is a decorator function in JAX. So it modifies, it wraps or decorates this function. And it's important because this does just-in-time compilation of the JAX code, which means that it can be slow to compute the first time that you run it, but then on subsequent runs, it would be very, very fast because it's compiled for your specific CPU architecture or GPU architecture, et cetera. So here we have a progress bar, which is the number of training steps that we want to do. And then we have this loop here. So we are generating a new noise on this line, and we are generating a new ground truth filtered noise. And what our training step receives is our input and our output, but we are trying to figure out what was the cutoff parameter that was used to turn X into Y. So it's like here, JIT hidden, it actually had a value of 440, and that's why it was able to do the low pass. But here, when we call it train step, it's on a different model. That different model was initialized with a cutoff of 10,000, but over time with gradient descent, it's being optimized to be a value of 440. Now, the line down here, where I call JIT train inference, it's actually returning two objects. The first one is the audio, but the second one is the human readable range of the output parameters. So going back to the discussion of normalized versus unnormalized parameters, these are the unnormalized parameters, and this is related to the SO function. So when we called SO, the architecture file took care of this for us, but SO was doing the work of making sure that mod vars contains our unnormalized parameters here. So let's run all of this. and we get a progress bar. You saw that the cutoff was starting at 10,000, and it's falling over time to 440. Should get there pretty quickly. Also, when I was running this on my Windows computer with a nice Intel CPU on it, this runs like 4 times faster, or maybe even 10 times faster than the CPU on Google Colab. So we ended up with the cutoff value of 440. Now let's plot it in the next box. So we're showing 2 graphs here. This is just the loss over time, the evaluation loss, and we plot it on 2 scales. So here we saw that the loss starts at 0.3 and it basically falls to 0. But on a log scale, it's kind of falling to 10 to the -4th and 10 to the -5th, and it's kind of getting stuck there. And that is just an issue where it's kind of zigzagging infinitely because we're not taking our step size, our learning rate step size, it's not falling to 0. So that's why you kind of get this zigzagging around 0. Yeah?
I have exactly the same curve. Why is it so reproducible?
Yeah, because we all probably have the same seed function. So, I mean, it's very high up here, but there's this seed value. I don't know where the first, yeah, here, I called it here. So if I were to change this magic number to something else, then we'd get different results. Yeah. You also, I mean, in JAX, you also have to take care that there's this interesting thing where whenever you're generating random numbers, you're always passing a key, but more specifically a subkey, because you take your key and you split it, and now everything that's downstream of that subkey is actually independent of the other key that remained. So it's this kind of a hierarchical key generation process that allows you to have, it's still deterministic, which is what you want because it's all based on a seed value, but it also just allows this very wide branching effect where it scales very well with random numbers. Okay, so we've generated our loss and it converged to 440. And as I mentioned, we were just using SGD, which is very boring, but there are more interesting optimizers in the Optax library. Okay, next thing that we're going to plot is the loss landscape. This is really important for debugging. So if your system only had 1 parameter, then you could plot this loss landscape. But if your system has 100 parameters, you might want to hold all of the parameters constant except for just 1, and then plot this loss landscape curve to get an impression of how chaotic the loss landscape is. Because that could show that machine learning, or at least by following gradients, could be a kind of hopeless endeavor. And you may want to rely on other methods like quality diversity or genetic algorithms or all the other opportunities for machine learning that don't involve gradients. Okay. So here we're going to do speed benchmarking on this next box. And what I want to talk about here is that we are comparing it against SciPy as our relative competitor. JAX is doing the same code that we defined earlier, which is a low-pass filter. But we're doing the same low-pass filter with the SciPy function L-filter. So I'm highlighting that here. L-filter is, does it stand for LTI? Or this is good trivia. It's an IIR filter. It takes the B and A coefficients that you can get from a Butterworth low-pass. And so I believe that this Butterworth low-pass is a 1. You can see I specify 1. And that's why it's a 1-pole filter, and that's equivalent to the Faust code that we specified earlier when I did fi.lowpass with a cutoff. So we're comparing JAX against SciPy, and we see that it's 2.57 milliseconds versus 7.14 milliseconds versus SciPy. So that's great, right? And what's even cooler is that SciPy, we gave it B and A coefficients, but actually we did a batch size of 100. So you could actually give different B and A coefficients to every item in our JAX filter. You know, we did just this Butterworth low-pass filter, but it could have had more arbitrary components, but the same number of components because it's a first-order filter. And, and we it would just be like varying the cutoff. That's what, if you change your cutoff value, then you get slightly different B and A values, but they're the same dimension size. And we would get different results in every item in our batch, but SciPy is only capable, to my knowledge, of having the same B and A coefficients used in every item in the batch. So JAX is faster than SciPy, but unfortunately, let's change this duration seconds to 0.5. And we'll see that on Google Colab, they become more comparable. Like they're roughly the same now, so the savings went away. But in my experience using a desktop computer, even when the duration is 0.5 seconds, JAX is still faster than SciPy. So I suspect that something is going wrong here in terms of the CPUs that are used in Google Colab, and it would be, you can get better performance relative to SciPy when you're using a Windows and, yeah, a desktop computer. Okay, so now we're going to move on to the cooler example from the morning talk, which was optimizing the cutoff automation. So cutoff is no longer a static parameter. It's actually a parameter that we change over time. So we define our code here. And here we are using the widget modulation, this relatively new feature in Faust, where we have our FX, but we are doing this arrow sign operator in Faust, and we are accessing the cutoff slider that exists, and we are doing this replace. But replace could have been something else. I think by default, it is an addition operator. So by default, it's probably, what? Multiplication, sorry. By default, it's this, but we are instead doing replace. So this is saying replace, cut the slider that exists inside, and then insert a wire so that you get a new continuous audio rate cutoff signal. So that is our new modified Faust code, and we convert it into JAX code, and now from our JAX code, we have our filter. So this is just a single filter. It's not meant to be a batch yet. It's just meant to process a single item and it has two inputs. It needs the filter cutoff. It needs a tensor in machine learning terms, a tensor where it has two channels. The first channel is the cutoff, and the second channel is the signal to be filtered. So we create our filter model class, and then we create a hidden model. And the hidden model is what we're going to use for we're going to give a ground truth automation, animation of our cutoff, and that's what the hidden model is. And now we create automation model. So this is kind of similar to what's going on in an architecture file, but we've coded our model ourselves. And I think that this looks maybe ugly to some extent, but I think it's definitely no worse than what exists in other libraries. I mean, sometimes you kind of have to get down to business and code a neural network architecture yourself. And this is just an example of that. So call here, underscore call, is similar in other machine learning libraries to the forward method in PyTorch or the call method in TensorFlow and so on. You always kind of have to implement something like this. So what is going on is we are creating a cutoff parameter, and we are going to, this cutoff parameter is a time series, and it's a time series of a length that we are specifying, but this time series represents our automation that we are going to optimize. So we could specify it to be the same number of samples as our audio rate, but that would be kind of expensive because it would be equal in size to the length of the audio. So if you were processing 1 second of audio, then this might be a tensor, a learnable tensor with 44,100 numbers inside it. But instead, you can work at it at a smaller cutoff array. So self.automation samples, this could be a smaller number. And then what we do is we clamp it to a safe range, and we remap it. This is what I mentioned earlier about why we used normalized parameters, because this is safer for machine learning. And then we remap it to our desired range of 20 to 20,000. And that that makes the filter stable. And now we do interpolation, where we take our time series, which might be small. It might only be 40 numbers, but we stretch it over our desired audio length. So T here is the input that has been passed to the length of the audio that we want to generate, which coincidentally is, of course, the length of the audio that has been passed to it. So then we do something where we have to expand the dimensions, and this increases the dimension size, and we concatenate our cutoff to our signal to be filtered. And so this is now a tensor with 2 channels on it, and we pass this tensor, x, into our filter model. So we create our filter model, and we give it a sample rate, and now we call filter model on x, and we give it the number of samples to produce, and this is our audio. So let's look at how we created it. So we said automation model, and we specify a number of automation samples. But what is automation samples? It's the length of the audio that we're generating, t. So that would be like 44,100 for 1 second of audio. But we've downsampled it according to this number here. So I'm going to first downsample this a lot to make it very apparent what is going on. So I'm actually going to do 1,000. And now I'm going to run this. Okay, so it didn't train yet, and now I have to keep doing the next box. And here it pointed out that our cutoff param shape was 44. So our cutoff animation that we're learning is just 44 numbers, but we're stretching it over, I think, 1 second of audio. And I'll keep executing the boxes, or the code snippets. Okay, so here we're doing the training. And it's training very quickly. It descended, but you can see that it's getting stuck at 0.01. And that's because our model doesn't have enough learning capacity to smoothly match the ground truth. So it trained, and I'll execute this one. And now we are going to get a plot, I think. So here, we got an animation, and it trained very quickly. But now if I pause, you can see here that this is not matching that peak very well, because our model's learning capacity was only 44 numbers for an entire second worth of audio. But let's go back and execute this one more time. So I'm going to automation downsample, and I'm changing this to 10. So that's 4,000 numbers, roughly. So it's more expensive to train. And I'm just doing shift return to execute the following code snippets. And it's training. Oh, you know, it's I think actually because I changed the number of parameters, the learning rate needed to change. So this is some live coding. So here, let's take our learning rate, and we will actually, I don't know, do it live. I'm going to change the learning rate and see what happens. Okay, it didn't work. Maybe I needed to go the other direction. What should I do? I'll do one more attempt, and then I'll just change the. I won't do such a large parameter. Oh, okay. This not quite working. Let's see what it looks like when it's done rendering. Okay. Didn't quite work. So I'm going to go back to our downsample, and I'm going to change this to 100. Execute, execute, and I'm going to change this back to -1, I think. Okay, so this is going to succeed. So yeah, because those are the numbers that I chose for the morning talk. But you can see upon visual inspection that it's matching the ground truth in blue much better. And I'll take a risk. Let's do something more exciting even. I will go to the ground truth, which is this blue curve, and I'm going to modify it. So let's find where that was. Here it is. So this is the frequency that I was using for that ground truth. So let's change this to double. So the number of cycles that you see here is going to double. And we'll see what happens. Okay, it's working. So yeah, the ground truth that we chose is totally arbitrary. It could be any array that you come up with. Now let's plot it. And there you have it. Even though the cutoff is much more chaotic in a sense, with the model's learning capacity was able to recover it. And it's not looking at the blue line. It has no awareness that the blue line exists because it's only looking at input audio and output audio, and the only thing it can change is this cutoff parameter automation over time, and yet it's able to recover the hidden latent signal of this cutoff animation to get the loss down to 0. So I think that's cool. Any questions? Yeah.
How do you explain the fact that it converges in this fashion, like the shape of the conversion, the shape of the conversion of the prediction? Is there anything to take from the?
I mean, it's cool. It kind of feels like it almost feels physical because it's like when you have a string and you just move you move the ends of the string upward, but it's kind of sagging in the middle. That's kind of what's going on here. I think there's no normalization going on here. So, for instance, when we coded our model here, we created this parameter. You could add an additional constraint in here where every gradient update, you have your cutoff parameter, but you could blur it. So every update, you would do a gradient update, but then each sample in your automation time series could be a convolution, a blur of its neighbors. And that would bring some stability so that you, for instance, you wouldn't have a totally chaotic prediction where the cutoffs diverge. And I think that when I showed that example where I think I downsampled, or I did I set the downsample to only 10. So it was 4,000 numbers. And I think that it failed because it diverged in a bad sense. And so as you, if you want even more resolution in your cutoff animation that you're inferring, you probably need to add some kind of regularizer. Is that making sense?
I was also asking myself why do the peaks and dips converge slower than the... But I think it's pretty hard because architecture is so complex.
No, I can explain that. So at some point in here, the cutoff is initialized. Sorry, where can I find this code? Oh, okay, so look at this. Our automation model, when we declared cutoff, we initialized it with a constant value of 0, and this is up to us. I could have changed this 0 to, let's do it one more time. I'm gonna change it to -0.9, in between -1 and 1. So let's look at our plot. So here, the orange line is starting in the middle, and I mean, roughly they converge at the same time. But let's run it one more time. And we're going to see that the orange line is going to start lower. And ultimately, I hope it succeeds. But I think that the bottom is going to be solved before the top portion is solved. Cool. It's working. So if you have some domain, knowledge about like an initial guess of what that parameter should be, the bad thing is you have to remap it into this -1 to 1 range because that's the correct machine learning technique to like make it more stable, I think. But you just when you're coding this yourself, you do that. But this looks like a pain, but I think it's just as good as anything else, any other library for this purpose, and yet we're still taking advantage of our low-pass filters and our oscillators and all the cool stuff that exists in the Faust libraries. Okay. Yeah.
You knew very quickly when it was failing, and I saw the error jump straight down to 0.01 before it and just hovered there. It was only like, a tenth of the rate overhead. Why is it behaving like that? And can you use that somehow to automatically know that it's failing?
Yeah, I mean, early stopping, for example, is like a solution to that. Like if it reaches a value of 0, that may be the wrong answer. It may just be a case of overfitting, and you may want to not use it. But sometimes it's actually like the right thing, and there might be something else that's causing it to explode. So I don't know the answer really.
The funny thing is it always failed a lot faster than it succeeded. When it succeeded, it was already very slow.
Yeah.
It failed, it always just jumped straight to fail.
Yeah. Yeah. Worth exploring more. Okay, any more on this? Yeah.
Can you take advantage of Faust also to generate the automation signal, for example, and the
Yeah.
input signal?
Yeah, for sure. So maybe Daydreamer is a handy way of doing that. Yeah. I mean, if you coded the Faust yourself, then you could have a JAX thing that produces the audio that is the hidden cutoff. And this is kind of what I'll get to later. So how much time do I have again?
I think you're already past.
Oh. Oh yeah, time was flying by. Okay.
Yeah, sorry. It's just that we need to leave the room by 6 this evening, and otherwise we're going to be like in big trouble. So.
Yeah. Okay.
So I just, and there are 2 more workshops. I mean, this is like super, super interesting, and I'm sure like everyone would love to continue, but I think we, unfortunately it's Saturday, and time is kind of limited, so.
Okay, very good. Well, just, do the collab on your own and make GitHub issues, email me, etc. Happy to help out. Thanks.
Cool. Thank you, David.